So, hello and welcome to today's training for students. We're gonna have a great topic today. It's the finite element analysis. It's a big topic for software companies, since the finite element analysis is kind of the heart inside a statics program. So that's like the overall goal for today, to understand the finite element analysis and to also use it and learn its restrictions within a program. At first, let me introduce myself for a bit. I'm Thomas Eichner, and I'm working for Dlubal Software in the development of the dynamic add-ons. So whenever you get in touch with seismic design, earthquake design, maybe a vibration analysis with bridges, or in general, whenever anything has to do with vibrations and you use a feature within RFEM, then I'm involved in the development of those features. In addition, I'm also working for the customer support, and that's all about me. So with me today, there's Paul Sevolgin. Paul Sevolgin is also in the development, and his field is the intersections between different programs. So for example, the intersection between RFEM and RStep, and with other companies' programs, for example, Revit or Tekla. So Paul will be here to answer your questions. So feel free to just type in any question you have. We're gonna get back to the questions. And so he's gonna answer your questions, and I'm gonna guide you through the finite element analysis and through RFEM. So maybe let's just cut off my camera here. So regarding the questions, right now we can see the GoToWebinar panel right here. You can adjust your audio settings right on top with this wheel. And if you have any questions, there's this question mark button also on top. And then you can just use it like WhatsApp or and just enter your question right below and send it. And then my colleague will reach out with the answer. If there will be any questions left throughout the end of the webinar, we will answer them until tomorrow per email. So no question will be unanswered. Okay, then let's start with today's training, with today's webinar for students. We will talk about the finite element analysis. That's the overall topic for today. So instead of only beams, we will also treat surfaces a lot today. Within this finite element analysis, we will go through the basic principles and also explain them with an introductory example, just a continuous lab, which we will model within RFEM 6. In the next step, we will go over the blade theory. In general, all the theory parts within this session, they won't be like too detailed, and it's just to keep you informed with the knowledge that helps for understanding the finite element analysis. The next part will be the nonlinear calculations. So there will be different ones, geometrically as well as structural nonlinearities. And for the last topic of today, we will treat the singularities, which are results in the system on which are just not really usable for design. And we will also treat measurements on how to counteract them. Okay, so let's start with our basics of the finite element analysis. As you may know from previous static lessons in your studies, there are two methods to calculate overdetermined systems. One would be the displacement method, and the other would be the force method. The force method, well, it's called force method since the forces are the unknowns in this solving process. Within the displacement method, we have the displacements as the unknowns. The displacement method is, in this case, more important for us since it is implemented within RFEM. So also most computer programs will use the displacement method. In general, the finite element analysis is used when an analytical solution of the structure is hardly possible. And that means we can't just create a function for, let's say, an 8-story building, which gives us the exact solution for every force we have there. Instead, we will take the help of the finite elements. And that's what we do with the finite element analysis. We're gonna take the real structure and we're gonna just cut it down or decompose it into a mesh of finite interconnected elements. So they're just like a specified amount of elements in the system and they are connected to each other then. We will see it in the next slide as well. There's some graphics for it for better understanding. Then what we also will need is to define the properties of the element continuum. We will have on the one hand connections between two finite elements, and within these connections we have like linked degrees of freedoms. I mean, you can imagine a plate connected to another plate, and at their intersection, let's say, the deformation in the z direction, so in the vertical direction, must be the same. That would be one example. The properties, so these exact solutions of these finite elements, will be calculated for the edges or for the corner points of these finite elements. Within these finite elements, we will use approximation sets to describe the internal forces, for example, inside one element itself. So one point, this decomposition of the real structure into a lot of finite elements, this is also called the discretization. And the discretization is a commonly used sentence or word for this process. And also in the literature, you will find this discretization quite a lot. So let's go on with our graphics here. Here we have it again shown in 6 steps. At first, we have our discretization. So we will have the mesh of the structure. We will have in this case, we have a slab. And the slab is now divided into these finite elements. These finite elements you can see in the second point here. Please don't be confused with this with these elements within the elements. They shouldn't be there, right? So these elements are the smallest already. These are all our small finite elements. For these finite elements, we can define the stiffness matrix, the element stiffness matrix, as well as the element load vector. So we have the system, if we only inspect one finite element, already known. And in the next step, we will combine all of those elements, and therefore we will combine the element stiffness matrices and the element load vectors into the global stiffness matrix as well as the global load vector. And now for the understanding, there's this static equation which is called K times U is F, which means the stiffness matrix times the deformation vector is the force vector. And now, due to assembling them to the global matrix and vector, we have this K as well as this F. But what's not known is the U, so the displacement vector. And that's what we want to get to. So let's go. Now we have the total stiffness, so the total stiffness matrix K. And in the next step, we will use our support conditions. We can see it there. And use it within the displacement vector. So, for example, for this edge of the slab, we have a line support. And this line support, well, it is fixed in Z direction, which means the line can't move in Z direction. And that means each entry within this displacement vector, which includes the location of this line hinge, must be 0. So we will build this in our equation system. And when everything is set, we can just solve this equation system. And that's done right here within our step 5. We will solve the equation vector. We will get our displacement vector. And with that displacement vector, we can finally recalculate our internal forces. So that's the whole process. And now we can just jump into the program. I will go rather slow today, so you can model along if you want to. And this would be the best moment to start RFEM 6 on your computers. So it's all set up when we start modeling. First, let's talk about our investigation, what we're gonna do in the first model. We're gonna investigate a continuous slab. So we see it right here. It's just a slab with 3 line supports, one in the middle and one at each end. And then we're gonna investigate on the size of these finite elements. We also will investigate on the impact of these size of the finite elements on the results. And for having a good comparison, we will also compare directly to a beam element, which you would also simply be able to calculate with, for example, the Schneider Bautabellen. So, okay, then I would say we can start with our first model here. So for it, we will create a new model. Right on the top left button, there's this new model. We will call it 01 continuous slab. And since it's only a simple plate, we can also let the program help us a bit. This means we can change our type from 3D to 2D XY plate. And when changing this, you will see how the degrees of freedom will change. Right here, we see 6 degrees of freedom. If we change it to 2D, we will see we're left with only 3 degrees of freedom. Because for slabs, those 3 are the only ones important for us. Also, we will only look at members and surfaces today, so no solids. And within that, we will also look for our add-ons for a second, since I will just deactivate our combinations. Since this is just not needed. We will just go and look at a uniform load of 10 kilonewton per square meter. So we don't need to combine any loading. Okay, and that's it. So we can press OK and find our empty model in the next step. There it is. So let's go with the view into the Z direction. We can go with our view cube or with those buttons here on top. That's pretty great. And there we are. So since we're gonna model together, or let's say to start from scratch, I will also delete all of my previous elements here. It means you just delete all basic objects. So there's no material defined anymore, no section, and no thickness. Now let's go with creating our first surface. Therefore, we could go here and just double click like the surfaces, or right click it and create new surface. What's also possible, and I mainly use this button since it's just the fast bar here on top. I will click on this button and then we can choose the rectangle. And if we used it the last time we created a surface, we will just click it and have the dialog opened. So, and with the creation of a new object, RFEM will guide you through everything that's needed for its creation. For example, we just want to create a surface. We don't have anything defined yet. We will press on OK, and there's our error. We don't have a thickness assigned. Okay, that means we need to create a thickness. The thickness can also be found here on the left side. You could create everything as well on this, just with this data navigator on this left side, but we're going to go through this dialogs for it. So we will click here for the thickness, and the thickness can be interpreted the same way as a section for a member. The thickness is nothing else than, well, the definition of the thickness of this plate, as well as its distribution over the area. We will stay with a uniform distribution of the thickness, and we will also go for, let's say, 300 millimeters right here. Okay, and now we see here another thing again. There's a material dialog, and here's already this create new material. That means next step will be to create this material. And now we will see that we could define all of our material values, well, user defined, or there's also this book on top. And whenever there's a book somewhere in the program, that means we have prepared a library for you. So you don't need to search all the material properties on your own. You can just click on the library, and you would also have regional limitations here. Well, we have most international standards, and you can limit what's shown here by just clicking on your region, for example. Let's just leave it as all. And since we want to investigate on a reinforced concrete slab, or let's say a concrete slab, we will go for C3037. So I will just enter C30 here, and there we are. We already have here the C30. So there are different standards for the C30, but whatsoever, we will go for Germany in this case. And if you can't find the Germany right away, you can just pick whatever C3037. I'm pretty sure there's no difference in any C3037. Especially for the Europe codes, there's no difference. I'm not sure if there's maybe another country which would have this C30 as well and define it differently, but they are just standardized over the regions. So it doesn't matter if you're just picking the German standard or the British standard and so on. So we're gonna take this one, press OK, and there it is. With another press OK on OK, we will have our material assigned, and then with another press on OK, we will have our thickness as well as the material assigned to this surface creation. And that's what we're gonna do next. We're gonna press OK to get back to our graphic interface. There we are. And then we will create a 10 times 5 meter surface. Yeah, why not like this? And there it is. So we have our slab right here. We can also look at it in 3D. We can use our display model settings for showing them, let's say, transparent or filled. This view is always good for, let's say, bigger structures when there are more surfaces under each other or they're overlapping kind of and stuff. So we can pick them better with this dotted or lined line here. Per double click on it, we can adjust it, but that's not needed right now. Also, we can see our base elements, so our material, our thickness, as well as our surface right here in the data navigator. Okay, that's great. Let's go for one additional display option here. You can define different renderings or different views as well in our display navigator right here. We could say, okay, don't show us any lines. Then let's go for this other one again. If we deactivate these lines, these corner lines will disappear. And with this, you can you have your own possibilities on what you want to see and what not. In addition, there's also this bottom here where we can influence our rendering. And if we go here on our rendering on this model, and then we see the solid model options, and further in the surfaces, we could also show them with the thickness. So that's just if you want to have more like an architectural view, and you could activate this. However, since it's a static program and we will use it for statics, this kind of 3D element, because like a real plate has a height as well, but in our finite element analysis, we will treat this as a 2D element. So it will have just 2 dimensions. Okay, let's leave this here. That's not needed anymore. So what we did now is we just created one plate. And this plate would just fall down right now. So what we need next would be our boundary conditions. And for those boundary conditions, we will also need a line in the middle of the surface. So that's what we're going to do. We're going to take this create line function. We're going to go in the middle on the top as well as in the middle of the bottom. And there it is. So our lines are set. We can also show it in our other display mode so we can see the line better. And now we want to apply our support conditions to those lines. That's completely simple. We're just going to take our quick button here on top. Or we could also go for our types of lines, for line support, and then assign them. However, since this is the most used tool here on top, and it's quite fast. We're gonna go for this procedure. Let's take it, and let's also look at this, suggested hinged line hinge. And now we will see the benefit of our early decision to model it in the plate dimension and not in the 3D domain. And that's quite simple. The program now helps us since we are in 2D plate. We don't need the deformations in the horizontal directions anymore. And we don't need the rotation about the Z-axis, which also would be kind of deformation in horizontal direction. So with this, we only really wanna hold like the Z direction on this lines, and that's already set within this preset hinge. Let's go for it. Here again, and then we will apply those supports to our lines. There they are. We can also apply the loading next, which will be just a uniform load, uniform surface load of 10 kilonewton per square meter. And with that done, we can just assign it to our surface here. Okay, and there it is. So our loading is done, our supports are done, our system is already ready for calculation. Just another hinge, just another hint. We can also adjust the size of supports as well as of the loading if we want to have it as changed. And yeah, then maybe let's just create our further plates for the investigation. Maybe you saw it already on the PowerPoint file. We will need 4 plates to investigate, which means we will go again and select everything within our current system. We will then right-click it and take the benefit of our move and copy function. Let's click here and let's also check this create copy button, which is really important. The next step, we're gonna copy it 3 times. We have a length of 10 meters. Then I want to have a space of 5 meters, and then there should be the next system. So we will need 15 meters. Now I just see from a previous model I had open, I'm still stuck with this millimeters here, the dimension of millimeters. I want to work with meters in the current model, so we can go for this units here on the bottom. We can click on it, and then already this red arrow will help us what units are used in the current dialog. And we see we have here lengths, millimeters, and we're gonna just change it to meters. Gonna prove it here and set our displacement for the X direction to 15 meters. When it's done, we can confirm it, and there our new models are. Now, what we see is that our grid is not over the whole system anymore. So we want to adjust also our grid here. And that can be done with a right click just anywhere on the screen and just click on the work plane and grid options. And within here now, we can say, okay, we have right now 30 dots, from here. That's not enough. What we want to have now is I'm just gonna put a lot of points here. Let's pick 200. Later on I will show you also this dynamically number of grid points. But we will also want a different spacing between those dots. Currently they are set to 1 meter. The problem with this 1 meter now would be that we won't have dots in the middle of the plate, right? So since it is 5 meters, the middle would be at 2.5 meters. That means I will adjust it and make our grid a bit more fine. Let's set it to 0.5 meter and apply it. There it is. Now we have our grid. Yeah, and it's quite better. Okay, so we have that. We can also look at our plates in 3D for a second. Let's go like this. Looks okay for this short duration of time. We just created 4 cool systems. At least simple systems. Okay, so in the next step, we will go for the Z view again. And as I previously mentioned, we want to investigate on this size of those finite elements. So maybe another hint, if you double click your middle mouse button from anywhere here, you will get back to the system and the screen is just adjusted to have all of your system within this window. Okay, so since we want to investigate on the size of the finite element mesh, we will also want to have those labs to have different finite elements. But at first, what is used if we don't define it for each surface? And without any assignment, we will have just our base settings here. This means we can look at them with this calculate button on top. And here we can find our mesh options and everything regarding the mesh. If we go for mesh settings right now, we will see that currently we have a length of the finite elements of 0.5 meters, which means these edges of those finite elements, well, the program tries to reach 0.5 meters with them. If it's not possible, then he will vary it and could also add triangular elements. But this would be you can also see it here, this length of the finite element. And this is what the size is tried to achieve by the program. However, we won't use this global settings at all, since we're gonna apply surface adjustments, surface refinement adjustments for every surface here. And since we are talking about surfaces, and that's maybe another hint, whenever you're talking about or you're thinking about modeling something, and this something can be assigned to a basic object, then it is kind of a property of this basic object. And that is where our types come into play. Right here, we have our types for nodes, for example, this nodal supports. We have our types for surfaces. There could be a surface supports. And here in this types for supports, we can also find our surface mesh refinements. And we will open it with a simple double click. And right here, we can now just create our surface adjustments, surface refinements. The first one will be quite coarse. We will go for 2 meters and assign it to our first surface here. We will apply it and create our next mesh refinement here. This will be only half the size. Well, the edges will be only half the size. And we will apply it to the surface number 2. And maybe you can see already, we created surface number 1, then surface number 2. So we can be smart and think about this as surface number 3 and this as surface number 4. Okay, so for the first two, we did click this and selected it in the graphics. For the next two, we will go with our faster way. We'll just enter surface 3 right here. Then we will go for the fourth one, and this one will be quite fine, and it will be assigned to our surface number 4. We will also see on which surface each mesh refinement is applied to here in the brackets. And now with OK, that's quite important, or the apply button first, but that's important. If you press cancel, everything we did within this dialog is not saved. So we will press OK. And before I press OK, I just wanna have this here. So you will see what happens right here. Let's press OK. And there it is. We now have a new rectangle within our surface. And those rectangles, we can see it also for every surface. Maybe like this. Shows us what the desired length of these, or the desired size of this finite elements will be. So here, our quite coarse 2 meters length. And here, well, we would have to zoom in to even see how big this element is. So that's really fine. Okay, so now we have the system created. Now we can go on and create a little helper for our interpretation of the results. Since surface results are not the best to interpret within the surface overall, we could also create a section through all of those continuous labs, and then we can evaluate the results just within this section. That's what we're gonna do. Now the section is no property of any basic objects. So it's not only like the section can cut a solid as well as it could cut a surface, and it's why it's not a property of a surface, for example. And for that case, we have something called this special objects. And within the special objects, we will find our result sections right here. We're gonna double click on it, and within this window, we could adjust in which directions this cut will work and in which direction it is displayed. Gladly for us, this Z direction is just fine, and we can go with all this predefined stuff. The only thing we need to define is from where to where does this section go. So kind of the boundaries of this section. And for this, we will use this 2-point selection right here. Go into the program, and I am a bit, I did this quite a lot in the past, so I don't need to zoom in to find the right node. And we can just go for the middle of both of the end plates. Let's go for this. Let's press OK, and let's turn the model for a second. And here we see it. Oh, maybe it's better to just use this -YQ. And there we see the section right here. Okay. So our surfaces are ready to go. Let's maybe show our filament of those surfaces again. And for the comparison, we said we also want to look into the results of a just simple constructed beam. That's what we're gonna do next. We're gonna create here this new member. And within this member, we will have to apply a section since we don't have any. It's like the same procedure as with the thickness before. Let's go for it. Gladly, our right material is already selected here. And we will have to adjust just the section dimensions. So, and what do we take here? For the height, it's quite obvious. We will take the same height as for the slabs. But now let's look at the other dimension of this section. We have 5 meters in the width of the plate. However, we now don't need a 5 meter section here. What we do need is a 1 meter, so 1000 millimeter section right here. And the reason for this is the results of surfaces are displayed per meter. And the results of members and beams are just shown in pure kilonewton. It's not kilonewton per meter, it's just kilonewton. So if we would have 2 meters here, it would be still just kilonewton. And so to have this per meter within the results of this member, we will just pick a 1 meter section here. Press OK here and also press OK here. Will get us back to a graphic user interface, and we will be able to create our 10 meter long member. This is done now. Now I see I have here some member representatives. They wouldn't be needed. Let's see if we can just deactivate them. I mean, like, it doesn't change anything. It's just, they are just some help, but I don't want to have this dot right here. Okay, now we want to have supports again, but we are missing this one node in the middle. So what we're gonna do is we're gonna right click on the member. We're gonna go for this member and we're gonna divide it with n intermediate nodes. There, just one is enough, and we can just create the division. If we would now press OK, then this member would be 2 members which are still connected here in the middle, but we can also use our on member nodes, so this member won't be divided. Okay, maybe as a hint, it wouldn't make any difference for the results. The only difference now is that we still have 1 member. We still have also, if we go for the basic objects, here still only 1 member. And it's, you can have fewer objects within your model with this. So also, if we hover over this node, we can see that it's defined with 50% of this member length, which also means if we now change this member in the length, also the place of this middle node will change. So we don't need it. So let's go back to this 10 meter beam and now apply our support conditions. So for this plate, we did only fix the Z direction. Now for the member, if we think about it, if we only fixed the Z direction of this member, that seems okay in the first step. But the problem is it could rotate around its own axis. This is not possible with this line hinge for the surface, since let's say supported here and here, so no rotation is possible. But with this point nodal support, we don't have this interaction kind of. So we need to also restrain this rotational degree of freedom. So we will go for this nodal support, and we will look at our predefined hinged one, and there it is. And now there's the point I just said. We will also have to restrain the rotational degree of freedom here. Now, we would only need to restrain the rotational degree of freedom on one end or on one node, and we wouldn't need it on the other two, but for simplicity I will just apply it to all three nodes, since for the results again it doesn't really matter in this case. Okay, so there's one more thing, and that's that we need to load the member in the same way as we loaded the surfaces. That means we will take our member load here on top. We will take it and just apply 10 kilonewton per meter to our member. When it's done, we have it right here. Okay, now our system is completed, but I just remembered I also want to have something different in the material. So now we want to change the material. There are different ways to go to. We could go per double click into our surface and go for the material and so on. That would need a few more clicks. The simpler way would go like this. We will take the material here, double click it, and we are in all the properties of the material. And now what I want to change is this Poisson's ratio. So that's kind of a value that describes the influence that, let's say we have a force direction, or not force direction, an internal force that makes pressure in this direction. This Poisson's ratio would give you information about how this internal action in this direction would influence the perpendicular direction. And since we are comparing everything here with each other, we don't really want to have this impact here. So we want to set this to 0. And that's only possible if we first activate this small user-defined material button. With this active, we can just change it to 0, and then we are good to go. Let's see at our self-weight load case here on top. Within this, we only have this one. We have our 10 kilonewton per square meter load in it. But here's also, that's just predefined by the program. It always creates a first load case with only the self-weight active. For this special case, it doesn't make, well, we don't need it. It's simpler to just have a 10 kilonewton per square meter load for interpretation. So we will just deselect this option. Okay. And yeah, right now we're done. So maybe to repeat a bit of theory from earlier, we have our plate, which defines our stiffness matrix. We have our loading, which defines our load vector. We have our supports, which have influence on our deformation vector. And with that, we have our equation, K times U is equal to F ready for its solving process. And that's what we're gonna do now. We're gonna go here and calculate this equation. Let's see what's gonna happen. Okay. So right now, from a first glance from the top, from the surface results, yeah, we can see quite some differences here. But with this view, well, as I said, the surface results with these colors, they are not quite simple to evaluate or to interpret. So we will go for the Y view right here. There it is. And now we can see the benefit of our sections here. We now have, like with this section results, something that we can compare quite better to our member results. We could also like change our deformation right here. See it right here. And let's stay with that. So next thing is we don't have any numbers on the left side. That's something that bothers me since it also makes the comparison quite hard. So to adjust this, we think about, okay, what results are they? They are from result sections. So we're gonna be in this result navigator on the left side, and we will look for result sections here. We have them here, but they are just for, okay, let us show the results or not. But we also have them in this menu on the bottom here. And with this result sections, we can say, show us all the values at local maximums and minimums, or just show us all values. You will see that's quite a lot for this one, but that doesn't mind since we see the most bottom one here as well, and that's the one we will compare. But let's see, no, I will change it to the local extremes. Yeah, that's fine. That's perfectly fine. So now we see a difference already. Maybe let's make it more clear. 1 digit is not enough. So we want to adjust the digits here. And that's done again with our units and decimal places. Right here. Again, our red arrows show us what is currently showed. And here we will go for 3 decimal places. There we go. And right now, the first thing we will see is the very fine finite element mesh. Well, it's almost the same as our beam element. So that's quite an exact solution. But now the next thing is, let's look first at the deformations and then at the internal forces. Or let's say, yeah, we will look first at the deformations now. We have here that kind of fits. This here, well, the difference is quite low, so I would say that's also precise enough. Here it gets to something like 10% already. And if I see like a 10% difference, in reality that could, yeah, that's maybe not enough accuracy for design, but it's also not too bad. But the problem comes now with this one. And that's quite a bit. That's like more than a fourth in difference. And that's not acceptable. Like this could lead to a complete collapse of the structure. I mean, this as well, but this is quite fatal. Okay, let's see why those results are like this right here. And therefore, we will go for the Z view again. And also, we will not show the results for this investigation. Now we see our constructed mesh. And we see this completely fine mesh. We will ignore it for the and we will just look at the difference between those three models. So in the first model with our 2 meters length here, well, that's quite coarse. And we also see we even have here a triangular element, which is also always not perfect, since it's just better to have like a uniformly distributed rectangular, we need element mesh. Sometimes it's not possible to evade those triangular shapes, but if possible, you should try to avoid them. So right here we have 3 elements. Now when we look at it, we could also assume, let's say, let's imagine a single span beam here. Then we know our maximum moment would be in the middle. But with this element in the middle, we wouldn't have any any result in the middle. That means we wouldn't even have the possibility to show us the maximum here, because the next value which would be shown would be this here at the edge of this element. So that's just not good. And that's the kind of point here in the next figure. We can see 5 elements here. I learned kind of some rules that in my studies, and the rules were like 6 elements between like supports for a single span beam should be good. You should use 6 elements between 2 supports, or also if you have a line load or a support load, you should also have 6 elements between this line load and the next support or line load. Like everything, there's a change in the boundary conditions or the force. There should be around about 6 elements to the next change. For design. For if you're just interested in looking at the forces that will get to your supports, then it could also be that just 4 elements are enough. But if you want to like remember something for the future, I would go for 6 elements. Okay, then let's look at the results again. And this time we will go for our internal forces. We will go for the member first. Let's go for the member right here. We will activate our MY, and there it is. Now we want to have the same result shown for our result sections. What I'm gonna do here is our result sections. I will define it to show the same results as I defined for surfaces. And I will go for our surfaces. There we have the internal forces. And well, we're showing the My for the beam. So let's try the My for the surfaces. But now we have a problem. They are, well, it's like not the same, right? It's just nonsense. And also we see the difference. We have for the coarse mesh, we have something, and for the fine mesh, there's nothing. Now for the explanation, we have different, internal forces conventions here. So for the My, it's quite simple. Our y-axis points outwards. This means with the right hand rule, we will know our positive My would be like this, pointing upwards. It's rotating around the y-axis. That's why it's called MY for beams. But now it's different for the members. And now, okay, before I'm gonna explain it, we will change to the right one. We will go for this MX. Now we see, okay, now we have comparable results. But why is that? Now for surfaces, this is differently defined. So it's called MX since we have the surface. We will go in X direction. And there's like a plane that's cutting through the surface now. And it's cutting in X direction. So perpendicular to the X direction. And then we rotate about this edge here, this free cut edge. And that's why, since the cut was done in the X direction, it's called MX. That means the MY would be exactly in the other direction. Okay. So let's go again for the Y perspective. We can also see here the results are quite similar. And let's not show the forces anymore. 31.18, 31.19. That's almost the same, but there will be some differences. And for this time, we will go for this section here. Now we select the section with a right click, and then this result diagrams. We will jump right here. There it is. And here we can just see the results for the different. It's just the same as we saw in the model, just that they will be next to each other and they could be better prepared for a printout report, for example. Okay, don't need this set. We're only gonna look at our results right here. And there we have it, 31 point something versus 28.45. That's some difference. That's like, in this case, I guess 10%. And this 10% also hold for the middle of the span here. And this 10%, those are not enough. I would say this result is just not precise enough. So here, maybe we can look at that here quite a bit better. So here this 28.45 versus the 31.818, yeah, almost 10%. That's not quite good. So that's the problem with this coarse mesh. We will lose exactness in the results. On the other hand, let's look at this extremely fine mesh. And let's also show again all values. Within the left system, we will see we only have 1, 2, 3, 4, 5, 6 elements here. So our global stiffness matrix is constructed out of the element matrices of 6 elements. We're just ignoring this dimension right now. Let's say we only investigate this direction here. So 6 elements. So this can be, excuse me. So this can be, quite fast be solved. It could also be almost calculated by hand, not like fast, but it could be. But on the other hand, if you look at this one, looks more like 100 elements. and this means also 100 kind of degrees of freedom here between each element. That means the solver and the calculation system is way bigger than in this first case. For this simple structure, it doesn't really make any difference since it's fast anyway. But if you think about like a 20-story building and you would go for a mesh which is fine like this, or if you think about my dynamics field where we not only have the spatial dimension but also the time dimension, and we're gonna calculate these equations once each 0.01 seconds, and we will increase our calculation time by quite a lot. So there's this one sentence, and that means for this finite element sizes, it should be as fine as necessary and as coarse as possible. Okay, so I would say we're already done with this part right here. And now we can go on for our next short theory. Back for our PowerPoint. There it is. And the next part will be the plate theory. So for members, you might know there are two concepts or two theories. The plate theories are almost the same as those for members. So for the beam element, we have the Bernoulli as well as the Timoshenko beam. The differences, well, let's go for the similarities first. The cross sections remain in place, and that's it. Now the differences, the cross sections for the Bernoulli beam remain perpendicular to the member axis, while for the Timoshenko beam, they won't stay perpendicular. You will see it in a few seconds in the next slide what that means. For the Bernoulli beam, we just don't care about the shear stiffness. Just don't care about the shear deformations, and it's just rigidly for shear forces. So for the Timoshenko beam, on the other hand, we will have an influence of the shear deformations. That means we won't only have this bending deformation, but we will also have an amount of shear deformation that's just added. So, and here is what I said with this, with this perpendicular to its axis geometry. For the Bernoulli beam, it will stay, well, the cross-section will stay perpendicular. But with our shear deformation in the Timoshenko beam, it will now deform just by this shear angle. So that's the main difference. And also, what you could see here is that the shear deformation gets, well, that the importance of the consideration of the shear deformation gets more important the, let's say, thicker this beam is, or let's say the higher this beam is right here. Because since this is a shear angle, the higher this height of the beam is, the bigger this influence will be. Okay, let's adapt this to our plate theories. And there's just different naming and a bit more, but mainly it's different naming. We have the Kirchhoff plate theory, and we have the Reissner-Mindlin plate theory. The Kirchhoff plane theory is, well, more equal to the Bernoulli beam. It has geometrically linear and small deformations. We have a linear elastic material law, the Hooke law. The cross sections remain flat and we don't have any warping inside these slabs. We have a constant thickness and we have this no consideration of shear deformations, like for the Bernoulli beam. Now let's compare the Reisner-Mindlin plate theory. The first 3 points stay the same, the first 4 points. But now there's the difference. With the Reisner-Mindlin, we now have a consideration of these shear deformations. And we also have a consideration of the transverse and lateral strains. So let's go for this one. Let's see at the transverse and lateral strain. Just as a reminder, we just set this mu, this Poisson's ratio, to 0 in our previous model. But now what's this Poisson's ratio? Well, as the title says, it's a factor that says on how the lateral strain will be for a force in its perpendicular direction. So for example, for the specimen, it's just a tension specimen and it will be pulled on both sides. So we will have it pulled here as well as here, and it will deform by delta L. Well, now with this Poisson's ratio, we define on how the section, in this case section, will shrink. So the change in the length will come from somewhere. And with this Poisson's ratio, we will define how much it will come from the other directions, kind of. So how much the impact of this longitudinal force is for the other direction. Okay, let's go into the plate theories again. For the Kirchhoff, we said no consideration of shear deformations, and for the Reisner-Mindlin, there is this consideration. Now, the Kirchhoff theory, it's the simpler one. It's, well, kind of better for hand calculations. But in the end, you would have tables anyway, and they are evaluated for both plate theories. So there may be no big difference anymore for hand calculations as well. But if you would try to solve it like a computer program, then the Kirchhoff would be way simpler. However, let's say the Kirchhoff theory, let's stay with the Kirchhoff first. It's called the theory of thin plates, since as we learned before, the higher the plate, the thicker the plate, the higher will be the influence of those shear deformations. That means this Kirchhoff theory is limited to thin plates. Also, we have this pure bending load bearing capacity, which means compared to the Bernoulli beam, that we also have had this deformation only from the bending and not from the shear force. And well, it's just a simplified approach. And with that being said, RFEM is not using the simplified approach. It enables it, but it's not using it. Okay, so let's compare the Reisner-Mindlin theory. It's more of the theory of thick plates, but you can use it for thin plates as well. So I would use this like always over the Kirchhoff. Then we have the component of the shear influence is relative high. Okay, that means the shear deformation needs to be considered, and it is considered. We don't have the error from not neglecting, from not considering the shear force. Here it's phrased a little bit different. It says, if we would use the Kirchhoff theory, we would have an error in neglecting shear force. Yeah, that means we need to use this because the error would get too high with the neglection if we don't use it. Okay, so just for this is the more accurate and better approach. There's the Reisner-Mindlin theory, just stay with it. But it could be that you need the Kirchhoff or some like comparison to a Kirchhoff plate theory for your exams or whatsoever. So I will just show you something in the program. Let's go into our self-weight load case for this. Let's go into our static analysis settings right here. And there we can go into this basic settings, and there we could change our plate theory. So if you're interested in calculating something with the Kirchhoff plate theory, then here's the place you could adjust it in the program. Like mostly you can also, for such findings of settings, I mean, this is quite a big program, and it has, at least for students, let's say, limitless possibilities. If you think the program can't like consider your investigation, and it's most likely that you just need to find the place where it is in the program. For that, it really helps to use our handbook, or let's say, for example, this Reisner-Mindlin and stuff. You also have this short helper here with our Mia, with our AI assistant. It's also on the homepage, and you can just write your question to her and she will send you like an FAQ or the direct link to the place in the handbook and so on. And then you just get like a GUI screenshot where you can find it. So that's like, I know time is rare, so this will help you be faster. Okay, then let's go back to the PowerPoint, but I think we're done there already. Exactly, so we're done here already, and that means we can jump back into RFEM. And for the next few models, you won't have to model along. I prepared some models already, so this is something you can just watch right now. And yeah, exactly. So we have right here a frame with tension members. What does it mean? That means we have nonlinearities. Just for one thing here, since we're treating nonlinearities, let's also define what a nonlinear calculation changes within RFEM. The biggest problem within those nonlinearities are that we can't use the superposition law anymore. Means if you remember, like the first semester, you would just calculate the first load case, let's say self-weight. You will get your moments, you will get your shear forces as results, and then you will pick your next load case and you will calculate it independently. You will get your results, you will get your internal forces, and for achieving the final result, you will just add them, because why not? And that's right for linear systems. The problem is now with nonlinear systems, this is not possible anymore. because the loading from the first load case can influence the system in a way that it changes its behavior for the other loading. And that's something that can happen with different applications. One would be the geometrically nonlinearity. That means if we have a geometrical linear system, we will apply a loading to a structure, and the internal forces will be calculated for the undeformed systems. So we only have we only need to solve the equation system one time. Now, a geometrically nonlinear calculation includes p-delta effects, it's the second order analysis. That means we will apply a loading to the system, it will deform, and then we will again investigate the deformed system under the loading. It will deform maybe quite a bit more, and we will repeat this process until this change in deformation is, well, extremely, or when this change between two iterations is quite low. So what we have there is we need to do this calculation multiple times. And this already gives the hint that it's gonna take quite longer than a linear calculation, right? Since you just have to calculate it again and again. And another possibility is the nonlinear material behavior. We will have an example for this later on. Another example would be the nonlinear behavior for elements, for hinges, for supports, for members. Let's take a support, for example. If you have a foundation and it's just lying on the ground, then the ground would take the pressure from this foundation. But let's say if we have some helicopters trying to pull the system up, the ground won't do anything to hold it down, right? It's only the self-weight that would hold it down. So the support would act differently in the one direction as in the other direction. And that's also a nonlinearity. Same effects could be implemented into members or hinges. Yeah, and this is the problem, as I said. We need to calculate the system multiple times. That means we have an increased calculation effort. Okay, then let's go into one model before our small coffee break. Let's go for this here, back to our model, back to our nonlinearity model. Right now, well, we have our system right here. It's just completely made of trusses. We have this frame which is completely made of truss member types. That means we have here hinges and all the members could rotate, well, about their connections here. They would also be free to rotate here on the bottom. So we have some wind loading in this case in the y direction. And now we want to see what's going to happen if we delete our tensioning here. And yes, let's just calculate it and see what happens. Okay, there's some error. Something seems wrong. Okay, here the stiffness matrix is singular. That means that's just a mathematical expression for the structure is unstable. means it would collapse. And it also gives us a hinge at this node in y direction. Y is here. So it would just fall down like in this direction, right? So all these members would rotate around their supports, and this would just go boom. Well, that's a problem. So we want to do something against it. And that's something we're gonna do with those, well, with those cables here. Let's look at them. What do we have here? On the left side, we have trusses with a nonlinearity. So we have in this case, we have a member nonlinearity. Let's look at it. Okay. Failure of compression already defined. Go into this member nonlinearity, failure of compression. There we have also the how the member would react to any forcing. If we get into tension, so a positive normal force, then we would have some stiffness in the member. However, as soon as we go into compression, the member is completely failing. So it won't take any load anymore. There are also different possibilities. Let's just check, for example, the yielding. This would mean it would go to this yielding limit, and then it wouldn't take any more force, but it would still be able to hold the current force level. Okay. Failure of compression, that's okay. One alternative for the truss with this nonlinearity would be to just select this tension member. It's just the same. So we have multiple ways to the right solution here. Let's stay with our truss. Let's press on OK. And let's see what the system does with our adjustment. Okay, and there we see something. Well, it's not unstable anymore. That's great. We see this force, this horizontal force, mainly travels directly into the support. We could also look at the support forces. Mainly goes, well, directly into the support. I would say 3.6 will go directly into the support with this member. The other 3.6 will be traveled through the beam here on top. And then we have this tension member, which will redirect most of the force back to the support. And what's with the other member here? Well, if we think about it, and if we look at our deformations as well, let's do it like this. Then we see this member, compared to its origin placement, it shortens. And if it shortens, that means it would have a pressure force. But we told the member to not be able to take pressure forces. That means it fails. And if you look closely, you will also see that the color changed. We have the blue tension here, and this one is gray now. And if a member is displayed gray in the results, that means that it failed. The same on the other side, just with a bit different values. It's the same here. This one takes the tension, and this member will fail. Okay, and that's it for this model. So I would say we could use a coffee break right now. So, well, let's do 10 minutes, I would say. Yeah, let's do 10 minutes and meet again in 10 minutes. So, see you soon. So, well then, welcome back. Then let's continue with another nonlinear investigation. So, with the next model, like I said, the next 4 models, you don't have to model along. You can just watch and interpret the nonlinear linearities with me. Let's go for our next frame here. What we can see is just a simple frame or one-way frame. We have some beams right here. This beam is just fixed in vertical and horizontal direction at the bottom, and it can rotate about this support. This top beam here, it's a truss, so it is kind of a hinged joint here, and it could also move to both sides without those cables in the middle. And in the middle we have, just as we did in our example before our break, we have a tension. Well, in this case we have a tension member type. So it can only carry tension forces and it will fail on pressure forces. So the loading is quite simple. We just have a vertical loading of 100 kilonewtons on both of these points. So let's look in our load case right here. We have a geometrically linear analysis setting here. So that's getting us to the next point of nonlinearity, and that's the geometrically nonlinearity, which we will investigate right here. Let's just calculate the model with this first order theory. And let's see, it's working. And now we see what happens here. We have the system, it's just gonna deform in vertical direction. That means these tension cables would shorten. That means they would need to take pressure, and that means they are gray now since they both failed. Now, what we want to do is a second order theory analysis. That means the program automatically adjusts a very small deformation in one direction and will investigate how the loading will impact, how this, let's say, imperfection will impact the analysis. So for it, we will go here and just change to our second order analysis. We will press OK, and also we will calculate the model again. And here we will see a problem. And the problem says we have an unstable model again, and this time it's in X direction, so this model would just fall over. Why is that? When we think about our first case, where we had the geometrical linear analysis, it deformed vertically, and those members shortened. They both failed. So what the program does now, within the second order theory, it will make this first calculation. Both members fail. And for the next iteration, where it is deformed a bit, we won't have these members anymore. That means with this deformed system, the next iteration would move it. And the next iteration would move it again. And it won't, the program won't be able to find an equilibrium for the system anymore, since it's just not like stable. So in reality, what would happen? We would have the force, the system would go downwards, both fail, that's okay. But the thing is, the system, when it deforms to the right side, there will be a point where this member would be under tension again. Since the system deforms again in this direction, the member kind of gets longer, and at some point this member is at its original length again, and from that point on it will take tension forces again. But this is currently not considered. But that's no problem, because we can just go into our static analysis settings right here, and we can go for this reactivation tab. And that's what we're gonna do. We're gonna add this exceptional handling. That's perfectly for those cases. That means we will only remove we will only have one failing member each iteration. So with this active and with a new calculation, we will now have a stable system again. Here we can see. And that's exactly what I mentioned before. Now the system deformed a bit, also in horizontal direction, because of the second order theory. And this member now takes tension forces. Well, they are incredibly low right now, since the second order effects are comparably low due to the only vertical loading, but this setting helps to reactivate this member again. So if you get into problems with instabilities and nonlinearities, then one setting option would be here within those reactivations. Okay, that's it already for the system. Let's just jump into nonlinear supports. So right here we have let's call it a cantilever. Without the support it would be. We have a cantilever, and that's forced with a single point load of 15 kilonewtons here on top. And we have a support that holds it right here. Okay, so for the comparison model, we added a nonlinearity to this support. Let's look at that nonlinearity. Here it is. And we can see in the x direction, which is also shown right here, in this x direction, we have a failing support now if the reaction is negative. So let's see here, just maybe one more hint. Our support reactions are always shown as external forces. We would have a force that comes to that support, and the support reaction is in the opposite direction. Just as a hint. Now let's look at the results. And here it is. So we can see for the first system, where we have this 15 kilonewton here, most of the force is directly taken by this support, right? We have this, let's maybe just go for another visualization. We can adjust our deformations right here and go it for only lines. This way we can see this 14.88 support reaction. The support direction looks in the positive x direction, but just as I mentioned, this is visualized as external force, and the force that really comes to that to that support would point in negative x direction, like the force we applied here. You see this 15 kilonewton? It's directed in negative x direction. So there will be a force to that support in negative x direction, and for that support to be able to withstand, well, or to have zero deformation, it needs to have a reaction force in the other direction. That's why this reaction force is defined in positive. But that's important now for our next system. Let's go for the sections again. And this time, this support will fail. And we defined the failing if the support gets like a negative x force. And that's what I meant, because now this would be interpreted as this 14 support force from the left system could be interpreted as a positive support force, and it's true. But for this nonlinearity, it's important what force is coming to that support, right? Okay, and maybe just for the last thing, I also changed the direction of the force, and if we change the direction, then the support is active again. You can see it here. We have forces again, and it's active again. Okay, so now we get to like two more interesting examples. Let's go on the first one. And that's a practical example. What we see here is just a simple ladder. This ladder just leans on the building, so it's only supported in x direction, right? So it leans to the building and it's only supported in x direction. On the bottom, it stands on the ground, so it is supported in Z direction. We could also implement a failure if negative, but that's not needed right now since we only have vertical forces from the top to the bottom, so it's gonna hold anyway, so this is not needed. It's also a hint for the future, like you try to model your system as simple as possible for your investigation. So you don't need to apply every nonlinearity there is, because it's just making things more complex. You just try, okay, what do I want from my model? And with this thought, you're gonna start modeling. So there's no like sense in over modeling, I would say it. Just model what you need and nothing more. Okay. So for the other two directions of the supports, we defined a friction. So with the friction, let's look at it in the x direction. We have this friction coefficient of 0.2. That means the support can hold 20% in horizontal direction of the support force in vertical direction. So if we have 1 kilonewton in vertical direction, then it will be able to hold 0.2 kilonewton in horizontal direction. And if the horizontal force gets higher, then it's just like yielding. Okay. With that said, let's go for our loading. We can see it here. Now we have a person of 100 kilograms, and this person is gonna walk. It's just gonna walk upwards on this ladder. Okay. Let's see what happens. We are just gonna calculate all, right? Maybe you could also think in the meantime, what happens with the horizontal force here needed if the person goes up. Okay. Now we see it worked perfectly fine until load case number 12. So let's see in the y direction what's happening right here. We have two supports on the bottom. That means our 1 kilonewton person does, well, the force splits into both supports on the bottom, and each support has now a support force of 0.5 kilonewton. 0.5 kilonewton, we had a 20% friction. That means 20% of 0.5 would be 0.1. That's the maximum possible horizontal force this support would be able to take. Now, when we remember statics from early on, we will see that with the equilibrium of moments around this point here, we have this 1 kilonewton with this eccentricity, and we have this horizontal force with this eccentricity. And due to the equilibrium of moments, we will now get an increasing horizontal force with each step we're gonna climb up. 6, 7. Now we will look at this, and we're interested in what's gonna happen with the 0.1 case. 8, 9, 10, 11, and here it happens. We can see a deformation of 14 meters now. Also, we have our warnings here. We can't find a result anymore. So the problem here is obviously that with the person on top, the ladder would just slip away. And that's not good, right? So there are different measures to counteract this, to make it possible for the person to climb higher. One would be someone just holds it, and we have two hands as horizontal supports, but that's not the case we're interested in. What we're interested right now is to have another person just standing on the lowest spross here. And that's what we're gonna simulate right now. We're gonna go for a load combination now. And with this load combination, we will go for one man or one woman on the highest spross and one on the lowest spross. Okay, we applied it. We also see what we're gonna simulate right now, and we can directly go into our results. So, and now it seems possible. And it's quite easy to explain. Just from these support forces, instead of having this 0.5 kilonewton per support, we now have 1 kilonewton per support. And that also doubles our capacity for horizontal loads within the supports. That's why we just proved that it helps that someone stands on the lowest spross of the ladder. Okay, let's finish with our last model for nonlinearities. And in this case, we will investigate tension specimen. Look at it from 3D. It's just modeled as one surface. For this surface, we have a fixed support on one side, and on the other side, we will just pull it. And we pull it with a specific force. In this case, this would be 503.572 kilonewton per meter on this line. So what is this force right now? What are we trying to investigate? Let's look into the surface for a second. It has S235 grade steel, and it's 3 millimeters thick. So we also have here a smaller height than on the right side. So we want to have the failure within this region. And now we did apply a load on the outer line, which is shown right here. And what we did here, the height of this line is 14 millimeters. So this here. So if we multiply this force times the length of the line, we will get this 7050 Newton. This height here is 10 millimeters. So if we take this force and divide it by the cross-sectional area in this region, we will get to our, what a surprise, yielding limit. Well, this was completely planned. I just did the calculation the other way around to get to this force. And this way we will simulate what happens if we go into yielding with this tension specimen. Right now, maybe we will look again into the surface. We have a material which is S235 and it's linear elastic. Okay, so we have a linear behavior of this material. Now within this first load case, 503.572, it's gonna be like simulated to be at the yielding limit. And for further investigation, we also added a load case, which is here with a 505 load, so just a tiny bit higher, a tiny bit over the yielding stiffness. And that's the two load cases we're gonna investigate now. Let's calculate both. And exactly, now we can see the results right here. Then we can see a deformation of 0.1 meter right here. We can also display it as an animation here. And yeah, quite simple, 0.1 millimeter. That looks fine. Let's look at our post-yielding situation. Well, it looks quite the same. It looks quite identical. Also, again, deformation of just 0.1 millimeter. So, for the stresses, I mean, it's a 235 grade steel. That means we can look up our stresses, and there we will go with our equivalent stresses. There we will go for these equivalent stresses according to Mises. Let's look at them. And now let's adjust also something right here. What we can see now is we have here our stresses given. Our limit, what our section would be able to do, would be 235. But we see now quite a some points that are higher than those 235. And we can just limit our limits differently. So the upper limit will be our 235. That means we will see everything over 235 will be 1%. And the lower one, yeah, we can just pick it as it is. And now we see 27% of this overall section gets over this 235 millimeters. Almost everything inside here. So the problem with this is the section should only be able to carry like 235, right? And 269 is quite a bit higher. It's not good. So we will investigate now in the next step the nonlinear material, the plastic material. One more hint with this results here. What you see is the finite elements, and the elements have all an equal value within the element. This is important when you're looking, well, when you're interpreting stresses as results, because you don't want the stresses to change within one element. That's what we can also show here. If we go for results, and one second, no, if we go for calculate and this results moving, there we can just adjust how we can see it. Right now we got this constant on the mesh elements. If we go for the continuous within surfaces, then it's following the line to our surfaces. It looks quite smooth, but it's not perfect for result interpretation. So this is cool for visualization, but not the best for interpretation. So we will go back and get it into the constant on mesh elements. Perfect. Now we're gonna do what we wanted to do. We're gonna look at our plastic material. It's this here. Let's also take a glance inside it. Here it is. We have a plastic material. The rest is quite the same as for the linear material, but we have an additional tab here on top. And if we click on it, we will be able to define the limits of this plasticity. Right now, for it, we will use the von Mises stresses. That's why I also showed you the equivalent von Mises stresses right here. And for them, we will define the yield strength, which is 235. This is automatically, everything here is just automatically done by the program. We have our elasticity modulus for the pre-yielding region, and we have a small stiffening afterwards. But you see, it's like 1/100,000 still of the initial elasticity. So with that, we can go into our results. Let's go for a calculation of everything. Also, you will see some convergence diagram on the right, which will have some more iterations, but it's fast anyway for this case. But what we see now, the yielding limit. In the other system, on that yielding limit, we already had some stresses that were beyond those 235 Newton per square millimeter. In this case, we don't have them. We just have 1.12%, which are these here, Yeah, if we would refine the mesh more and more, this would tend to 0. So we would really have only the limit value within this section. So, but let's look at our deformations. Our deformations for the yielding limit and plastic material, they are 0.1 millimeter. So the same as with elastic material. Now we will go for our past yielding loading. We click it and oof, that's something different. Now we have 8.2 millimeters. So like 820 times the deformation we would have with a linear material. And also what we see within that deformation, let's look at it in our animation. It will also shorten. You see it right here. So in the cross-section plane, it will shorten. And that's with the Poisson's ratio, which we had in the first part of the webinar. Okay, but that's quite different, right? So as soon as we have, well, a trespassing of those yielding limit, we shouldn't go for the elastic material anymore, or we should increase its limit at least, or change a different material, let's say it that way. Also, now we're interested, okay, which elements are yielding in this case? That's something we can also investigate with RFEM. We could go for our criteria here, and there we can go for our plastic criteria. So right now we see everything as estimated within this region in the middle is already in the plastic region. So in the second part of this bilinear material definition. Also, for sure, we can watch at our equivalent von Mises stresses. And there we will also see this 24% here on top. They lie between our yielding limit and a higher value. The higher value is not that much higher, right? This is due to our post-yielding stiffness, which is just 2.1. That means we won't have just like one line here which takes every force now, which could be possible with an elastic material model, but with this very small elasticity modulus, everything here needs to take its part for taking the load. Okay. All right. So this is like everything for non-linearities. And now we can get to our last part of the day. And this will be our singularities. So let's go into PowerPoint again. Singularities, well, what are these and where do they occur? First, they occur at points of discontinuity in the calculation model. The problem is they deliver no meaningful results. It's a model problem and it's not a physical problem that really occurs on site. We will get infinite stresses and infinite internal forces. A mesh refinement will not improve the result. Contrary, it most likely will just increase the singularity. And for RFEM, or for in general, there are different locations where singularities can occur. This is one's point and line nodes. Also point and line supports, which are from the physical understanding kind of the same. And at openings and re-entrant corners, as well as when the stiffness makes jumps. So for example, when the stiffness changes due to a material change or let's say a thickness jump, that's also a situation for singularities. So all of these points I can explain to you further in the next model. And if you would like, you could again start out from 6 and try to model along. It's gonna be, from the modeling, it's almost the same as our first model. So we can go through this a little bit faster. And for it, we're just gonna create us a new model. We're gonna go for 2D XY plane, and we're also again don't use the combination wizard and the load wizard. The name would be something like, let's say, 7th example, call it singularity of a single load. Okay, and that's it. If that we have our model right here, we can go into our Z direction view and just create our stuff as we did previously. Let's create our surface again. Okay, I don't have our material here, so I will just search our C30 again. If you model with me, you should have now this material already saved from our first model. I just opened our tension specimen in between. That's where I got those materials imported from. Okay, we're gonna go with this concrete and we're gonna go, let's make this 200 millimeter in this case. Okay, we're gonna press on OK, and then we're gonna make this slab just like 8 times 6 meters. Now we want to investigate a point load. That means we're gonna just place it in the middle. Well, we're gonna place a node in the middle of our slab, and on that load we will apply a 100 kilonewton nodal force. So we have our stiffness matrix defined, we have our load vector defined. No, I think I deleted load, that's not good. There it is again. Now we need some boundary conditions. Let's put in just some predefined line supports to every line in the system. And well, that's it already. We're gonna do the same as in the first model today. We're gonna copy it about 3 times. And with a displacement, oh, here comes the millimeter again. Let's change it to meters again. And since they are this time 8 meters, we're gonna displace them by 10 meters. 3 times, that's good. There we have it. Well, this grid, we don't need to see it right now. We don't have any use for it. So we're gonna just deactivate it here on the bottom. So the next step would be the surface refinements. And that's something we also learned some speed here already. Let's go for 2 meters for surface 1. The next one will be 1 meter for surface 2. The next one with 0.5 meters for surface 3. And the next one Okay, let's not go too small. Let's go for 0.25 meters for surface 4. Okay, we see the rectangulars again, and we also want our result section. Means we're gonna go for special objects and then this result section. Just define the two endnodes for the result section here and here. Okay, there it is. And then we're good to go. We just need to deactivate our self-weight again. And then I'm just gonna start the calculation right here. Okay, there we have it. Can look at our deformation. Can look in our y direction again. Let's show our local extremes. There we see. Okay, the deformations seem quite good. 2.3 everywhere. So we can't see the singularity, at least for deformations. But let's see what happens if we're looking at our bending moment. Let's activate the MX. And now the singularity takes place. So for the left side, we have here 37.17 kilonewton meter per meter. Compared to the right side, we have the 52. So I think an estimation of 20–30% more. That's quite a lot. Well, 50% off this one, but yeah. And for the design, I mean, what value would we use now to calculate the needed reinforcement in this case? Would we go for this 52? Would we go for this 37? What's right here? And that's a well, often occurring problem in practice, because we need a design, right? So we need a approach to design these differences. And there we have some approaches for. And for this approach now, we will go into our result section itself. Let's go right here and result diagrams. There it is. And now we can just go for result smoothing. That means we see the peak here and we see the triangles here. So it seems like this is more pointy than this one. And now we want to think about what if we integrate this moment here. And that's what we want to do right now. Also, if we have a point force somewhere, we could think about it as, in reality, it won't be a point force. It won't be a needle where some force is going downwards. Mostly it will be like a column of dimensions 0.5 meters times 0.5 meters. Also, we have a thickness of the plate, which means the force can also kind of distribute due to the thickness, and therefore the peak is just not useful anymore. And for trying to consider the reality, we can now add this moving right here, and add it accordingly. Right now we will go for a region of 1 meter that we will smooth it, and this region we will apply to all of those floor surfaces. So the last one with 27.5 and 28.5. You can press apply. So it's okay. There we see now here we have 31 as the integrated value. And yeah, now we don't have like a 30% or 50% difference anymore. Quite the opposite. We can see here 31, 31, 31, and here 28. So it seems like for this design, it would be most economical to use this value here. And also me myself, I would just design now with this smoothed value. But also if you like have not just a coarse mesh, the difference is not too big. So you could also design just for this 31. But as you can see, it's sometimes important to do some investigations on the size of your finite elements. Okay, let's quit it here and go into another approach for counteracting those singularities. And one other option would be that we don't apply these nodal forces. Let me just copy this load case. And in the next step, we will assume there's a column on top with dimension 0.5 meters times 0.5 meters. And that means we want to have a loading which is also like this, which is an area load and not a concentrated load anymore. So let's go for this new free rectangular load. And this function right here is exactly what we want. We want to have column dimensions of 0.5 meter. And we want to have a center point right here. Then we also need to assign it to a surface right here. So surface 1 with the center this and the column dimensions of this. Now we can apply. Oh, I forgot the load value. And the load value would be, let's go for a formula here. And this is now, let's see, 100 kilonewton. That's what we had as a point force, divided by 0.5 meters times 0.5 meters for the area of this new, column. It's done, and we have a result of 400 kilonewton per square meter. We can apply it, and there it is. Now we're going to repeat it also for the other surfaces, and therefore we only select the node and the surface and apply next. There it is. And this same procedure we're going to repeat 2 more times. This is okay. Surface 4, well, we need this node here in the middle. And there it is. So let's calculate already. And let's see what our results do. Let's go in the y direction. And what a surprise, it helps us. It helps us extremely. And it also correlates with our smoothing range, right? This one is a bit smaller than the rest now. We have 30. I think with the smoothing rate, we had round about 31, maybe here 28. And yes, that's quite cool. One other thing, of course, you could also like combine those two variants. So we could use this result now and also smooth it over a certain range. So that's one possibility or two possibilities to counteract singularities. Okay. And now we're gonna treat our last investigation for today. Therefore, we will need a new model. And we're gonna pick this time 8, and there we're gonna go for nodal support singularity. Again, I will just deactivate everything that's not needed to the existing plate. That's okay. Let's go. And there it is. Again, we're gonna go for 4 slabs here. Let's just start right away. This time it's quite easy. The only thing I wanna change is here. I wanna go for 300 millimeters again. Okay. And stay with these C30, 37. Press OK. And then we can, create our system with, let's say, 8 times 4 meters. And we will want a nodal support right on the left-hand side, so at 2 meters and 2 meters. We will want to have a line support on one side of the surface right here. And we want to have a nodal support just in Z direction right here in the middle. Okay, we can also adjust the size here a bit. Okay, next step, just as before, we're going to load it with 10 kilonewton per square meter. And we're going to copy all of it in the same way, 3 times in 10 meters. Okay, there it is. Then we're going to add our surface refinements, mesh refinements. Same way as before, 2 meters for the first one, 1 meter for the second one. Oh. Now I was kind of too fast because I did it for 2 surfaces here. Okay, 1 meter for the second surface. Copy. 0.5 for the third surface. And for the fourth surface, we will go with 0.25. Okay, that's what we have here. The last thing missing is our special object, which is our result section, defined by 2 points. And okay, so it's done already. Let's go and deactivate the save rate again and calculate it already. Okay, let's go in the Y direction again. Maybe this time we can go with the view cube. There it is. Let's also have our all values here. There we see. Now we see the problem with this mesh here. Well, an exemplic problem. We see on the finer mesh, we see our maximum of 1.7 millimeters. Kind of right there. With information, we don't need them. We have this 1.7 millimeters. This 1.7 millimeters would be in between this 1.3 and 1.4, but we don't have a result there, means we just forget some internal forces to investigate. That's a big problem. So we need to have at least 1 or 2 points in the vicinity of these maximums. Okay, that's one problem we can directly see from these deformations. But let's see at the other point, and that means let's see at our result sections, which should be the same results as our surfaces. And there we want to have our mx again. And what's happening here? We have 46. We even have a jump here. That's not really right. That's due to there's only one element here. So here the results are obviously wrong. And in the other ones we see it quite better. But the problem is above the nodal support, let's deactivate the loads, we have again a value that gets higher and higher the finer the mesh is. So for those singularities, we would have the same options as before. We could use the integrated values, like the result smoothing, or we can also go and edit our support. This is quite similar to the case where we just transferred the nodal load to our surface load. But right here, we can go into our nodal support, and we could either just add a spring constant. This would make the support flexible, and it would be able to deform vertically. The problem is it wouldn't help with the singularity, since this is not really a statically overdetermined system. I mean, it's a plate, and it has one support on the right side and one support on the left side. So it's all, we could call it statically determined. And with that said, if we add here some flexibility of this, well, not flexibility, some deformation capacity of the support, it would be able to deform like in that direction. But it would have to take the force anyway, because the force can't go anywhere else. That's only possible with statically overdetermined systems. That's the reason why it wouldn't help in this case. But what would help, what can help, is that we add a imaginary column, a fictitious column. And this column can be defined in the step. We will go for a column of 3 meters. We will also see the values change at each input. We will go for material of C30, a hinged column base. And what it does now is the program calculates like equivalent springs right below the support, which are calculated from the geometrically boundaries of the column below. And we can also define if it should be like this. This is now a surface like support, or if it just should be this one elastic nodal support, which I just mentioned won't get us too far ahead right now. So we will go with this elastic surface foundation. Okay, let's apply it. And let's go into our results one last time. So, okay. Now, what can we see here? I mean, it's quite better than before, because we had here around about 90. We don't have results now for this elastic support, since it just goes into the support here already. but this is at least, look at the difference here, 4 difference here. I would compare those two, those are fine. This one, maybe the system is still too coarse, I would say. And this, we can forget this anyway. So this helps a bit, right? Maybe another results moving would also help. I think the results moving, my opinion, had the best impact on our singularities for the day. Okay. Maybe one last hint about singularities. I mean, the problem with singularities is due to the finite element size. Let's think about this. Well, for example, this nodal support here. We see now this white rectangle. And we have a force here. If it's a nodal force or it's a nodal support, that doesn't matter. In the end, for the system, it's just a pointy force for the system. So the problem is the pointy force must be, it must develop over the space. So right now, if we try to apply it to this rectangle, we would have a pretty big area it could go to. But the smaller these finite elements get, the smaller we get here, the smaller the force can distribute around. And if it's infinitesimal small, then our reactions would tend to infinity. And it's mathematical correct, but physically it's just not gonna happen. Because we never have one pointy needle in those systems. And if we had, then the needle would just punch through this slab. Okay. And that's it for today. Let's maybe just revise what we did. We did look into the finite element analysis and its principles, how the procedure is within programs as well as in general for the finite element analysis. We looked at it in RFEM 6, and we looked at the impact of the finite element lengths on the results. Then we investigated the plate theories, the difference between the Kirchhoff and the Reisner-Mindlin theory. We said that the Reisner-Mindlin theory is the standard, it's the better approach, and it's used in the programs by default. We also talked about nonlinear calculation, if it's geometrically nonlinearity or material nonlinearity. We investigated several examples for it. And in the last part, we did look at some singularities and how we can counteract those. Okay, then let's go one last time to the PowerPoint here. And yes, as you see, we're always happy if we find some working students. And as I introduced myself in the beginning, I told you I'm working on the product engineering for the dynamic add-ons. And I can just say it's remarkable how much I was able to learn here. The combination of this customer support and the theory within the product engineering, I think no studies would have gotten me where I am right now, brain-wise. And also the customers will reach out to us with customer models. So where other engineers like spend a year of time to create a model and to think about how it's possible to simulate something, they ask us for help, and we see this model which others have a year of time invested, and we can just see all of this information in a few days, and we can learn so immensely much from them, and that's really great. And for me myself, dynamics, I love dynamics, so this is perfect. So if you're interested, just visit our homepage, go to the career page, and look if you're interested. Okay, so now we're done for today. And yeah, I wish you good luck on your further studies and have a nice evening.